is used to predict and optimize building energy performance. It aids in design decisions to enhance efficiency and reduce costs. Best practice guides such as ASHRAE Standard 209 or SIPSI TM54 or Neighbors Design for Performance Guide explain how to undertake modeling correctly. These and other similar guides used globally aim to enable better performance projections and to ensure that holistic analysis is undertaken for better informed design decisions. For example, let's look at ASHRAE Standard 209. It establishes minimum requirements for using simulations to assess building performance and to inform decision making. As per the standard, modelers are expected to undertake design refinements related to building fabric and systems and an iterative modeling process. Additionally, some of the modeling cycles in the standard require sensitivity analysis, uncertainty assessment, and design optimization. For example, cycle 3 in the standard requires iterative modeling to assess load reduction by various strategies. Similarly, cycle 4 on HVAC system and control analysis at schematic design stage. In addition to this, there are 2 modeling cycles that require parametric modeling specifically. First is the modeling cycle 1 that requires doing a sensitivity analysis to determine which building characteristics affect the performance the most. On a simple box model, you will need to assess sensitivity for changes in the building design, such as those related to window to wall ratio, orientation, and building envelope. Similarly, modeling cycle 6 requires performing multi-objective optimization using genetic algorithms to find the best design options. You first identify optimization objectives, variables, and constraints. The objectives and constraints can be cost, energy, carbon, or comfort parameters, and design variable options can include window to wall ratio, U values, shading, HVAC equipment, etc. DesignBuilder optimization and other parametric tools within the software are fully equipped to handle all standard 209 modeling requirements. Other documents such as TM54 or Neighbors Guide supplement and complement standard 209. TM54 provides guidance on projecting energy use during design stage and has similar modeling requirements. It specifically mentions that modelers should undertake sensitivity analysis and test for various scenarios, especially for minimizing risks when buildings are procured under energy performance contracts. Similarly, Neighbors Guide provides a framework for ensuring buildings achieve performance targets with modeling at its heart. Among the various modeling requirements, one significant aspect in the Neighbors Guide is that the base case model should be varied to explore buildings' resilience to real-world risks, such as those that relate to occupancy, operations, controls, or maintenance. As with standard 209, DesignBuilder parametric tools are configured to handle all these easily. Parametric modeling is a process where one or more design variables are changed and their impact on building performance is assessed in order to identify the best design options that will maximize performance. There are various ways to undertake parametric modeling, and different tools can be used depending on the purpose of the modeling. For example, parametric analysis, which is a brute force method in which all possible combinations of design variables are tested. However, optimization and sensitivity analysis would be considered advanced tools because they can surgically search and reduce the search space, thereby providing a more efficient way to identify best design options. Let's explore these one by one. Starting with parametric analysis. As mentioned, parametric analysis is a brute force method of changing parameters sequentially and running simulations for the entire search space. It is commonly used to generate design curves or histograms which show how performance parameters like energy, cost, and comfort can vary as design variables are adjusted. These design curves help communicate the impact of design decisions on building performance effectively. For example, the graph shows impact of changing window to wall percentage and overhang length on the cooling load. So with 4 options for window to wall ratio and 5 options for shading, the parametric analysis has design curves with 20 simulations. In this parametric example, the graphs plot variation in carbon emissions and compare it with the various window to wall ratios for each line representing the different glazing types. In the next example, we can see the impact of changing window to wall ratio and the heating set points on the building's annual heating load. Using these design curves, you can select an optimum configuration for the building design. Parametric analysis can also be used to assess the impact of future climate scenarios. In this example, the impact of future climate on occupant comfort in the building is assessed. Weather data is the design variable, and the output or the key performance indicator is discomfort hours. Other key performance indicators such as cooling energy or peak demand could also be assessed. The parametric examples we saw explored 1 or 2 variables with a handful of design options. Total combinations or the search space consisted of a few dozen simulations. Then what happens if there are many variables and design options? The number of combination increases exponentially. The size of design space is multiplication of all the options of all the variables. So if I assume that there are 10 design variables with 4 options each, the number of combinations would be 4 to the power of 10, or like 4 multiplied by 10 times, 4 multiplied 4, and which will result in more than 1 million design variants. And if each simulation takes about 1 minute, then simulating the entire search space would be very time consuming, even with parallel computing. So we need an efficient method. And the answer is optimization. Optimization enables you to search the whole design space quickly and effectively to find the best combinations of design variables. It does this by using genetic algorithm, which operates on the survival of the fittest principle of genetic natural evolution. Using this advanced algorithm, optimization gives the design team confidence that they can have identified all strongest design solutions within the search space. This is what a optimization process flowchart looks like. It starts with setting the objectives, constraints, and variables. Objectives are the target outputs, often called key performance indicators, and typically include outputs such as energy, cost, comfort, and unmet load hours. Constraints are the upper or lower limits of the key performance indicators. This helps the optimization engine to avoid searching for solutions that you don't want, such as those you can avoid that exceed your project budget or that exceed the hours where set points are not met. Variables, as you know, are the model inputs which are changed as per the design options. Once the optimization is set up, then the analysis can start and simulations are run in batches. Genetic algorithm assesses each batch of results to find the best solutions and then uses that information to generate the next batch of simulations. The process is automatically repeated until all likely strong solutions are found. Once the optimizer stops finding optimum solutions, the process finishes. And the optimization results look something like this. The X and Y axis show the objectives for the process which we are optimizing. In this case, we are trying to minimize the net energy consumption and capital cost. The points here show the performance of all simulations that were run during the optimization. Each point value is an individual simulation with unique combination of design variables. The white points show the valid solutions that aren't optimal, and yellow points are the ones that have a failed constraint. The red points on the leading edge of the point cloud, called the Pareto front, represents the solutions that cannot be beaten by these objectives. I'll show you a short video to illustrate how Pareto front develops for a small model with two objectives, 3 design variables, and there are no constraints here. The process is sped up and gives a great insight into how the optimizer works. Progressively, stronger solutions are created, resulting in a dense cloud towards the origin. These simulations are done in batches and they can use parallel computing. DesignBuilder parametric tools are designed to use all available cores on your individual machines or on your server without limitations or restrictions from the software. So that covers all the main points about the optimization concept, and let's examine some of the applications in real-world case studies. I'll start with this simple house project by Arturo Ordonez of Solar. The project aims to significantly reduce construction costs, carbon emissions, and environmental impacts of new build house in Spain. Designers had around 170,000 possible design permutations to explore. Therefore, optimization was used to search the design space for all optimum solutions. The goal was to find the best trade-off between design variables, including window-to-wall ratio, thermal mass, insulation, glazing, and shading. The graph shows cost versus carbon trade-off for the house. 7 optimization runs, one for each building form, are shown by different colors. The results show that the first 2 building forms offer the best performance. They are closer to the Pareto front. The graph here shows only the Pareto fronts of each of the 7 building forms. We can see that overall optimization solutions correspond to one of the first 2 building forms. The second building form in the list was selected for further analysis. Within the Pareto front of the selected building form, 3 solutions were chosen. Solution 7, 11, and 18 marked here. These are in the middle of the Pareto and avoid extremes. The design option that forms solution 7 and 18 provide carbon and cost-friendly design options respectively. And the design options related to solution 11, the design options are well-balanced selection. Lessons from these were used to inform the final design. The final design refined using optimization was significantly better than typical and previous projects. It was much cheaper and also less carbon intensive. The project obtained highest energy rating according to the Spanish Building Technical Code. This case study and others I will be showing today are documented on DesignBuilder's website. So at the end of the webinar, I'll show you how to find them. We now move to the next case study, which Brendan Hall of CHA Consulting in Syracuse, New York, shared with us. This example shows an optimization problem where we can use not just at the building level, but also for building's individual elements such as the HVAC system. The project completing by Karpinski Engineering focused on optimizing the balance between heating and cooling loads in a ground source heat pump system. This is because heat pumps provide both heating and cooling, and if sized optimally, they can save significantly on plant costs. This becomes more important in ground coupled systems where heat rejection to and from the bore field has a big impact on size and cost of the ground loop. In this project, modeling and optimization processes identified combination of energy conservation measures that have significant impact on the total loads considering the whole picture. So while ECM1 provides the lowest cooling load, ECM2 provided the lowest heating load. However, the optimum solution of ECM5 provided the lowest combined effect. Therefore, with ECM5, the ground heat exchanger length was reduced from 19,000 feet in the base case to under 14,000 feet in ECM5. This offsets the cost for other energy conservation measures to improve the design further. This is an excellent example demonstrating importance of intelligently combining key design variables for maximum impact. This graph shows a novel application of optimization. Here, optimization is used in advanced stages to identify optimum control parameters for building HVAC and other systems. The study is centered around what is the earliest allowed start time of the boiler that minimizes both occupant discomfort and building heating load. We know that earlier the heating system can be switched on, the less discomfort occupants are likely to feel on the coldest mornings of the year. But more heating energy would be consumed over the year. So to do this optimization, system start time was not a standard design variable, and therefore a custom variable was created using our scripting tools. Exploring the option of starting the system between 7 a.m. to 1 a.m., the optimization results indicate that there are diminishing returns regarding comfort when the earliest start time is much below 4 a.m. Even in peak winters, switching the heating on around 5 a.m. seems to be the sweet spot. This simple example shows the powerful capabilities of using scripting tools within DesignBuilder and optimize one or more operational settings in the model or even within HVAC system. This is another example of using optimization. Optimization and parametric tools can also be used to assist with model calibration. You can create custom outputs using scripts, and these custom outputs can be error metrics that are used in calibration, such as CVRMSE and NMBE. Then optimization engine will look for design options that minimizes those errors, and the results can be visualized with parallel coordinates, and design options which meet those error thresholds can be considered to calibrate and fine-tune the model. Moving on to the next case study, Gaurav Shori and his team at PSI Energy Private Limited in New Delhi, India, shared this with us. In this project, the designers intended to clearly understand cost effectiveness of various design options and to safeguard energy efficient solutions against value engineering. This study, similar to the house study we saw earlier, deals with a much larger building with a much more complex optimization problem with many design variables. The design objectives in this case were to minimize cooling demand and maximize the capital cost. Design variables selected were related to construction assembly, external finishes, shading design, and space and conditioning and lighting systems. Envelope variations explored options related to U value, thermal mass, and covered walls, roofs, and windows. Shading is a low-cost way of reducing solar gains in place of high-performance glazing, and DesignBuilder's target option was used, and different shading combinations for different orientations were explored as design options. Besides U value, the external surface finishes were also considered for the envelope. Scripting tools were used to define solar absorptance of the outermost material as a non-standard custom variable. On the system side, various options for lighting and HVAC systems were also considered. The options here were those that were selected by designers, factoring in operational and maintenance issues. All possible combinations of design variables selected result in a search space of over 1 billion options. The complete optimization run is shown here. The optimization was run for about 3,000 simulations and took approximately 36 hours. Analyzing the results and point cloud, the project team answered key questions related to trade-offs between system efficiency and envelope performance, use of shading versus high-performance glazing, and they also assessed the most efficient shading strategy for each orientation. We can see that optimization problem for this case study was very complex. There were large number of variables with numerous combinations. So while this analysis was completed in acceptable timescales, the actual process would be done much more faster now by using sensitivity analysis as a pre-screening exercise for optimization. So what is sensitivity analysis? We know that all model inputs are our best estimates and they contain uncertainties, such as those that are related to construction quality, user behavior, or weather data. Sensitivity analysis is a study of how variation in model outputs can be attributed to uncertainty in the inputs. It's often used to report which design variables have the greatest or least impact on the simulation results. So it can also tell us what the relationship of the design variable is with the output, whether they are directly or inversely correlated. Typical applications of sensitivity analysis include assessment of causes of uncertainty, in modeling results due to changes in input or variations, such as how occupant behavior or construction quality can impact total energy use. Then designers can take high impact corrective measures to minimize those uncertainties. It can be used in risk assessment to achieve design objectives and if there are any preset performance targets. It can also support model calibration by identifying the main factors that lead to operation stage performance issues. Another application which we will discuss now is the use of sensitivity analysis as a preliminary step to an optimization exercise. Sensitivity analysis can help remove unimportant design variables from the study to simplify the analysis and reduce simulation time. So how does it all work? Sensitivity analysis can determine which are the most influential design variables first and what the relationship to the output is. Then based on those findings, users can remove all the non-influential variables from optimization runs. If the variable is influential for only one of the objectives, its value can also be predetermined and sensitivity analysis can be removed from that variable can be removed from the optimization. Therefore, if focusing only on important variables, then the optimization results are cleaner, quicker, and easily understandable. Let's see how this applies to our recent case study. These are the sensitivity analysis graphs for design objectives of our last case study. One for cooling energy and another one for cost. They show which variables are more important than others for each of the objectives, ranking them in order of importance. This list summarizes the importance ranking. Variables are highlighted based on their level of sensitivity. Variables with low, medium, and high importance are marked as red, yellow, and green respectively. With this ranking and following this decision matrix, design variables in optimization were reduced from 12 to 6. And if we compare the two approaches, then we end up at the same answer. Optimization results with 12 design variables, which you can see on the left, took longer computation time, whereas the sensitivity plus optimization approach took less time because 6 of the variables which were there in the previous run were screened out using sensitivity. The optimization exercise at this point only had 6 variables to look into, and therefore we can see that running a sensitivity analysis as a precursor to optimization makes optimization more effective and reduces the simulation time. This is an exciting example that shows using strength of different parametric tools at different stages can make modeling even more effective. At the end of the webinar, I'll be showing you how to find more details about this case study on our website. This is the last case study I'll be discussing today that shows another application of sensitivity analysis. The project is a performance contracting project. It aims to achieve a performance rating of A as a part of energy performance contract. Contractual performance targets are quite a powerful way of delivering and ensuring that buildings perform when they are constructed. However, committing to such targets requires engineers to consider the risks and implications carefully. The study shows how uncertainty analysis can quantify the risks associated with meeting performance targets, and sensitivity analysis can be used to manage these risks. The building was designed to achieve a A rating with a performance target of 18.78 net carbon emissions per year. These are the risk factors that the project team identified during the risk assessment discussions. These relate mainly to construction quality, design specifications, building operation related issues. Assuming typical variation in risk factors based on design team's past projects and previous experience, the building's net energy consumption projections were very uncertain. The actual energy use would range anywhere between 16 to 27 kilogram carbon per meter square per year. Comparing it to our target of 18.7, the project team realized that under current business as usual practices, the building would likely fail to achieve the desired performance. Something needs to be done to reduce this uncertainty. So the next step was a sensitivity analysis. Sensitivity analysis was undertaken to rank the risk factors according to their importance. The results highlighted the factors that have significant impact on the building's carbon performance. This revised list of risk factors in decreasing order of importance was referred to by the project team, and they were ensured that extra safeguards are kept in place to ensure the high important risk factors are constantly in check and are tracked as the design and construction of the building progresses. So if those safeguards, these additional safeguards, they were factored in, the revised uncertainty range of the building was calculated, and it showed that the building would fare much better. The uncertainty would be reduced from a very wide margin before to between 16 and 21 kilogram CO2 per meter square per year. Comparing it to our target of 18.7, the project now had more likely chance of meeting the target even with all real-world uncertainties. This example therefore shows that sensitivity analysis and uncertainty quantification methods can help you manage the risks in building performance in a systematic and quantifiable way. These are all the cases I'll discuss today, but I'll show you how to access these case studies on the website. But before I go to the website, I'll summarize the key features of various DesignBuilder parametric tools. So first, starting with tool-specific features of parametric analysis. Here, parametric analysis, you can run multiple simulations automatically, adjusting up to 2 variables at a time to create design curve outputs. These design curves can be very useful as a part of design process to understand how buildings performance is affected by variation in buildings configuration and operation. Parametric analysis comes as standard with our simulation module. With optimization, we use genetic algorithms to assess trade-off between various design options and their impact on environmental performance. DesignBuilder optimization allows you to navigate easily the complex relationship between design objectives, constraints, and possible design options. You can optimize for any number of design variables and options for up to 2 objectives while reporting any number of other additional outputs. DesignBuilder optimization is fully integrated with the main software and meets all the standard 209 optimization cycle requirements. Optimization results can be analyzed in different ways. They can be done by using point clouds, which we saw before, or also by using multiple charts, parallel coordinates, and bubble plots. The current version of DesignBuilder provides point cloud results, which can be exported. Bubble plots and parallel coordinate graphs tools, which you are seeing here, are in advanced stages of development, and they will be available in near future for beta testing. So please keep an eye out for the announcement in our newsletter and on our LinkedIn page in the coming weeks and months. Finally, uncertainty and sensitivity analysis in DesignBuilder can generate high quality reports with histograms for each output and input, explaining the significance of various results. For the input parameters, various sampling methods and wide range of probabilistic distributions are available. And as the case was with optimization, all standard 209 requirements are met, and any number of design variables can be included in the analysis for each of the selected outputs.